Hello, everybody, and welcome to class. Today, we're going to start our journey through modern college mathematics, talking about problem-solving strategies from Chapter 1, Section 1. We're often told that mathematics is a set of tools for solving problems. So, we begin our study of mathematics with a look at what solving problems actually means. The modern approach to problem solving was first introduced by George Poya in How to Solve It. This book, published in 1945, puts forward the 4 steps to solving a problem. Understand the problem, devise a plan, carry out the plan, look back at your results. And we're going to come back to this over and over and over and over and over in this course. In 2016, researchers at Carnegie Mellon University used neuroimaging techniques to show that these 4 steps are linked to 4 different parts of the brain. Step 1, understand the problem. It makes sense that before you can actually solve a problem, you must first understand what the problem actually is. Take the time to make sure that you understand what is known about the situation and what you are asked to determine. Rewrite the given information in your own words. Draw a picture if it might help. Using or drawing a figure can be a very useful tool for solving many types of problems. If a figure is provided, look at it. Draw on it if necessary. If there is no figure, think about if there is anything in the problem that it might be helpful to see. Your sketch does not need to look good. Any visual might be able to help you think about the problem. Step 2, devise a plan. Once you know what you need to do, figure out how to get there. This is usually the hardest step of the process. If you do not have a plan on how to solve the problem, it makes no sense to dive into calculations. Yet, somehow, many students try to skip this step and just start plugging numbers in without thinking about what the numbers are actually representing and how they relate to each other. Usually, this step is the most challenging part of this process. The ideas presented throughout this course will be looking at how to apply different strategies to solve problems. Step 3, carry out the plan. Now that you have a plan, it's time to do the work. This is usually the easiest step of the process. This is also usually the only part of the process that involves doing math. And then step 4, look back at your result. Once you have your result, look back and make sure that the result makes sense. Let's take a look at example 1. Clara's apartment, indicated by a filled dot on the map below, is near the corner of 2nd Street and B Avenue. She wants to go to the store, indicated by an open circle on the map, near the corner of 5th Street and E. How many different direct routes could she potentially travel to make this trip? We'll take a direct route to mean that Clara never travels away from the store. In other words, all of her movements are headed in the direction of the store, never backtracking. Step 1, understand the problem. We already have a map indicating our starting point, Clara's apartment, and ending point, the store, with streets named. Step 2, devise a plan. As we look at the map, we can mark places where Clara can make a decision. If we map all of them, we can come back and count them later. We may start at Clara's apartment and work forward, or we might start at the store and work backwards. Step 3, carry out the plan. From Clara's apartment, we know that she needs to start by walking on 2nd Street to C Avenue. This is the only move that we have from the starting point that heads towards the store. If she went left, she'd be heading away. It's not a direct route. We also know that Clara needs to finish the trip by walking on E Avenue from 4th Street. We can mark that on the figure. Why? Because it's the only way to get to the store that is a direct route. If we're coming from any other direction, that means that we had to have moved away from the store. At 2nd and C, Clara can choose to either travel along 2nd Street down to E, or turn and move along C Street to 3rd. From the end of the journey to get to 4th and E, Clara must have either traveled along 4th Street from D or traveled along E from 3rd. These are the only two movements that get us to this position right here, 4th and E. Coming from any other direction would have meant that we moved away from the store. It wouldn't have been a direct route. We mark 2nd and C with a dot to indicate that Clara must make a decision at this intersection. At 2nd and E over here, the only choice is to continue along E to 3rd, meeting with the rest of the path. At 3rd and C right here, Clara must travel to 3rd and D. Why must she go to 3rd and D? If she goes down to 5th Street, she's past the store. She would have to backtrack to get to it. Continuing all the way down C to 5th Street would not be a direct route. We have to join up with the other path that we had. So once she gets to 3rd and D, she must choose to either keep traveling along 3rd Street to meet up with this path, or from 3rd and D, she can go down D and meet up with this path. So the only choices that Clara makes are at 2nd and C and at 3rd and D. The reason those are the only choices is because any other path in any other spot would not take a direct route. So 1, she can continue on 2nd until E and then take E all the way to the store. If she instead turns on C, she could either take 3rd to E, then take E to the rest of the way to the store. That would be path 2. Or she can turn again on D, again on 4th, then turn on to E to take the last block to the store. So there are 1, 2, 3 different direct routes to the store. And that's looking back at our result. Be careful. Of course, the most important tool for problem solving is to read the problem carefully. Sometimes you have far more information than you need, which may trick you into trying to answer a more difficult question. Sometimes there's an easy to miss piece of information that can make a problem simple to solve. Let's take a look at example 2. Sam has 3 brothers. Ned is 3 years younger than her. Evan is 2 years younger than Ned. And Bob is a year younger than Evan. How much younger is Evan than his eldest brother? Step 1, understand the problem. We know about 4 siblings. Sam, Ned, who is 3 years younger than Sam, Evan, who is 2 years younger than Ned, and Bob, who is 1 year younger than Evan. We're asked to find Evan's age relative to his eldest brother. There's one piece of information that's hidden in the statement. Sam is referred to as her in the second sentence. Many people reading this situation miss that and assume that the story is about 4 brothers, not 3 brothers and their sister. So I've carried the information over to this next slide. We have it up here. Step 2, devise a plan. First, we need to identify who Evan's eldest brother is. Then we can use the information provided and some arithmetic to find the age difference. Step 3, carry out the plan. From the description, Ned is the eldest brother, then Evan, then Bob. So we only need to know the difference in age between Evan and Ned. This is given in the problem as 2 years. Evan is 2 years younger than Ned. So we didn't even have to do arithmetic. It was actually given to us once we figured out the order of the brothers. Step 4, look back at your result. Evan is 2 years younger than his eldest brother. Creating organized lists. Several different kinds of problems can be solved by listing the possible options. The key is to keep the list organized so that you can be sure that all possible options actually appear on the list. We don't want to miss any. We don't want to double any up. Here, we will organize lists by looking at all of the possibilities for each choice in succession. Example 3. How many different ways are there to answer the 4 questions on a short true-false quiz? Step 1, understand the problem. This quiz has 4 questions. Each answer is either true or false. And we want to know how many different possible ways there are to answer the 4 questions. Step 2, devise a plan. Since there are only 4 questions, we should be able to list out all of the possibilities. To save space, we will write the test as a 4-character string. For example, TFTT means the first response is true, the second response is false, and the third and fourth responses are true. Step 3, carry out the plan. To keep our list organized, we will focus on changing one option at a time from the right to the left. We'll start with every response true, then change the 4th response. So T, 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 T. Then we'll change the last one on the right, T, 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 F. These are all the possibilities that start with 3 trues. Now, let's look at those that start with true, true, false. We did all the true, true, trues. So we change the last one on the right to false. We would have true, true, false, true, and true, true, false, false. Those are all the possibilities that start with true, true, false. Now let's look at those that start with true, false. True, false, true, true. True, false, true, false. True, false, false, true. True, false, false, false. These are all the possibilities that start with true, false. Finally, we'll look at those that start with false. False, true, true, true. False, true, true, false. False, true, false, true. False, true, false, false. False, false, true, true. false, false, true, false, 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 true, false, 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 false. And these are all the possibilities that start with false. Now, I might have lost you. That's okay. This is not an easy pattern to come up with. But if we put these all in a list, when we look back at our result, notice the pattern that developed. We counted 16 different possible ways to complete this quiz. The number of outcomes raised to the number of events there are, the 2 outcomes, true, false, raised to the 4 questions, 2 to the 4th, would be 16. And here are 16 possibilities that we came up with. So it's actually possible, first, to come up with the number of possibilities there are, and then this wonderful pattern. Look at the 4th entry in the pattern. True, false, 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 true, false. It alternates. Look at the 3rd column. True, true, false, false. True, true, false, false. True, true, false, false. True, true, false, false. It alternates. Look at the 2nd column. 4 trues, 4 falses. 4 trues, 4 falses. And then looking at the 1st column, half of them were true, half of them were false. So if we were to figure out outcomes raised to events, that there's 2 to the 4th, 16 different possibilities, we would write out 16 spaces, and starting from left to right, half true, half false. And then of the ones that were true, half of those are true in the 2nd spot, and half are false in the 2nd spot. And then of the ones where the 2nd column was true, half of those are true, half of those are false. And then the ones that were true in the 3rd spot, half of those are true, half of those are false. So there's this alternating pattern that developed here. But as far as the example here goes, we were tasked with coming up with how many different possible ways there are, and we came up with our 16 by listing them all out, trying to be diligent, that we're not missing any, also that we're not repeating any. Starting simple. One other common approach to solving problems is to first find a simpler related problem to solve. Then you can extend your solution to the problem at hand, either by modifying your existing work or by finding a pattern. Example 4. At the start of a meeting, each of the 12 attendees shakes every other attendee's hand. How many handshakes take place? Step 1, understand the problem. There are 12 people in the meeting. Every person shakes every other person's hand. Handshakes always involve exactly 2 people, and if I shake your hand, you also shook my hand. We need to know how many handshakes are involved. Step 2, devise a plan. We can try to solve this problem by creating an organized list. However, it may be too complicated at the start to ensure that our list is organized. So we'll first solve a simpler problem where there are fewer people at the meeting and see if we can find a pattern. So step 3, let's carry out this plan. One person cannot be considered a meeting, so the simplest meeting involves 2 people. Call them Alice and Bob. When only 2 people meet, 1 handshake is sufficient. Alice and Bob shake hands, 1 handshake. More complicated than 2 people is 3. Let's invite Carol to the meeting. Alice and Bob still shake each other's hands, But now everyone also shakes Carol's hand. So there was that one handshake between Alice and Bob. And then Alice and Carol shake hands, and Bob and Carol shake hands. The one we had plus the two more gives us 3 handshakes now. Now a fourth person joins, Dan, a D name, how convenient. The 3 handshakes between Alice, Bob, and Carol still happen, but each also shakes Dan's hand. So we had our original 1 handshake, and then we added 2 more to give us 3, and now we're adding 3 more to give us 6. Alice and Dan, Bob and Dan, Carol and Dan. You may be starting to see a pattern. If you are, make a prediction as to what will happen next. When Aaron, E-name, walks into the meeting, the handshakes between Alice, Bob, Carol, and Dan still occur, but everyone also shakes Aaron's hand. So we're adding 4 more. So we had 1, then we added 2 more, then we added 3 more, then we added 4 more. We certainly can solve this problem by inviting Frank, Grace, Harold, Irene, John, Kelly, and Larry to the meeting in turn and listing all of the handshakes. However, if you see the pattern, we can save a lot of time. When the nth person walks into the room, they need to shake hands with the n-1 people already there. When Erin walked into the room, she was the 5th person. She had to shake hands with the 4 people already there. When Dan walked into the room, he was the 4th person. He needed to shake hands with the 3 people already there. The 3rd person in the room shook hands with the 2 people already there. So the nth person walks into the room, they shake hands with the n-1 people already there. So when we invite a 6th person, there will be 5 more handshakes. That brings us up to 15. When we invite a 7th person, there'll be 6 more handshakes. That brings us up to 21. When we invite an 8th person, there'll be 7 more handshakes. 21 plus 7 brings us up to 28. We need to get all the way up to inviting the 12th person. So we invite the 9th, the 10th, the 11th, and the 12th, which adds 8, 9, 10, and 11. Oops. And we end up with 66 handshakes. So step 4, looking back at the result, there will be 66 total handshakes between the 12 people at this meeting. In this last example, we used what's called inductive reasoning to solve the problem. We saw a pattern in how the number of handshakes grows as more people are in the meeting and predicted that this pattern would continue. We need to think about how and when it's safe to use inductive reasoning. Sometimes the pattern that you think you see is not really there. The human brain is very good at recognizing patterns. If we're careful about how we use it, inductive reasoning can be a powerful problem-solving tool. For example, to find the next term in the sequence 3, 6, 9, 12, 15, question mark, you may notice that this sequence can be explained by adding 3 to each number. 3 plus 3 is 6, plus 3 is 9, plus 3 is 12, plus 3 is 15. Or you might have identified the pattern as the multiples of 3, 3, 6, 9, 12, 15. Either way, the answer is 18 because these patterns are the same mathematically. Of course, there's nothing that says that a pattern in numbers must obey some sort of arithmetic rule. The next example illustrates a different kind of pattern that appears in numbers. Find the next term in the sequence. 1, 1, 1, 2, 1, 1, 2, 1, 1, 1, 1, 1, 2, 2, 1, 3, 1, 2, 2, 1, 1, Question. At first glance, there's no obvious pattern in these numbers, and with how quickly they grow, you may have little hope of finding a simple calculation to go from one to the next. Instead, we need to think outside the box with this pattern. I didn't say 1, 11, 21, 1,211, 111,221, 312,211, because that would actually make this more difficult to figure out. I said 1, 1, 1, 2, 1, 1, 2, 1, 1. And that's kind of a hint at how we would have to think about this pattern. The first entry, 1, is written with 1, 1. The second entry, 11, is written with 2 ones. The third entry, 21, is written with 1, 2, then 1, 1. So again, how many things do we have here? We have 1, 1. Now how many things do we have? We have 2 ones. Now what do we have? We have 1, 2, and 1, 1. 1, 2, 1, 1. That's the next number. And it's written with 1, 1, 1, 2, and 2 ones. 1, 1, 1, 2, 2, 1. That's the next number. And it's written with 3 ones, 2 twos, and 1, 1. 3, 1, 2, 2, 1, 1. That's the next number. Well, now we know how to find the question mark number. This sixth entry is written with 1, 3, 1, 1, 2 twos, and 2 ones. So the next number is going to be 1, 3, 1, 1, 2, 2, 2, 1. This sequence is called the look and say sequence, and it's surprisingly well studied by mathematicians. Now be careful. The problem with inductive reasoning is that finding a pattern does not necessarily mean that you have found the right pattern to make an accurate prediction for your situation. The pattern may simply not have enough information to make a prediction. For example, consider the sequence 2, 3, 5, question mark. Is it +1, then +2, then +3? If so, because 2 + 1 is 3, 3 + 2 is 5, 5 + 3, the next number would be 8. Or maybe it's times 2 minus 1. 2 times 2 is 4 minus 1 is 3. 3 times 2 is 6 minus 1 is 5. 5 times 2 is 10 minus 1 would be 9. So is it 8? Is it 9? What's the pattern? Maybe it's actually the list of prime numbers, 2, 3, 5, 7, 11, 13, 17, 19, 23. In which case the next number would be 7. Without more information, there's no way to determine which of these patterns, if any of them, actually describes the sequence. This is why it's important not just to predict the next number in the sequence, but also to explain where that prediction comes from. If you say it's 7, then you need to say because of the list of prime numbers. If it's 8 that you're saying next, then you should identify that it's because it's +3 in the sequence +1, +3, or sorry, +1, +2, +3, +4, +5, +6, etc. If you say it's 9, then that's because it's times 2 minus 1. A final example. Consider a circle with points spread randomly around it and lines connecting all of the points. So if the circle has just one dot on it, there are no lines we can draw. You can't draw a line from a dot to the same dot. So this is one region inside the circle with one dot. If the circle has 2 dots on it, we can draw one line connecting the dots, which divides the circle into 2 regions. If the circle has 1, 2, 3 dots on it, we can draw 1, 2, 3 lines connecting all of the dots. This divides the circle into 1, 2, 3, 4 regions. If the circle has 4 dots on it, we can draw 1, 2, 3, 4, 5, 6 lines connecting all of the dots, which divides the circle into 1, 2, 3, 4, 5, 6, 7, 8 regions. We seem to have a nice doubling pattern for the number of regions with 1 dot, 2 dots, 3 dots, 4 dots. We started with 1 region, which doubled to 2 regions, which doubled to 4 regions, which doubled to 8 regions. So we can guess that we're going to get 16, 32, and 64 regions for 5, 6, and 7 dots. Let's see what happens. When the circle has 5 dots on it, it takes 10 lines to connect all the dots. And the lines divide the circle into 16 regions. So our guess was correct for 5 dots. However, and this is not a mistake, when we have 6 dots, it takes 15 lines to connect all of the dots, but the lines can only at best divide the circle into 31 regions. Our guess was 32. But in actuality, it was 31. Our pattern doesn't hold. We no longer have a guess for what happens when there's 7 dots. So just because the pattern starts does not mean that it continues. This is the unfortunate downside of inductive reasoning. It's still a powerful tool, and when it comes to making predictions, inductive reasoning is really the only tool that we have. But before using any tool, it's important to understand what it cannot do as well as what it can. It actually turns out, point of interest, that the number of regions which can be created by connecting n dots around the circumference of a circle is determined by this weird looking formula right here. N to the 4th minus 6n cubed plus 23n squared minus 18n plus 24 all over 24. Despite our best intentions, this is never going to be a formula that we can find by looking at patterns. Thank you for your attention here in class today, and I will see you next time.